morning.
Good morning.
How are you today?
I'm fine, Mrs. Kwasha.
Oh, well, thank you. How are you?
I'm good. So today we will discuss data types and descriptive statistics, and then see whatever discussion points will arise from that. So when you look at data collection processes, the next thing that we want to do once we collect data is to be able to describe that data and generate information from that data. And the most basic statistical process that we can go through in order to understand what is characterizing our data in terms of our study participants is the area of descriptive statistics. So in descriptive statistics, we are basically describing our data so that we understand the data generating process, understand how our study participants in terms of the source population is being characterized in terms of the data that we'll collect. So we will discuss the different data types that we encounter in research, and also discuss the measurement scales and data presentation techniques, as well as the summary measures that are used to have an in-depth understanding of our outcomes, of the variables of interest in a study, so that we can generate useful information, come up with valid conclusions on what is characterizing a population of interest. So basically, when we talk of descriptive statistics, we are talking of summary measures that can come in numerical form, or in the form of tables, or in the form of graphs, that will help us look at patterns in a given data set. So this helps us to summarize the information that is contained in the data of interest. And then also descriptive statistics also help us to present data in a way that communicates information, in a way that communicates for the reader to have an understanding of the characteristics that are found in the population of interest. So an example of a descriptive statistics presentation techniques is that bar chart, always showing data in the form of quotas that could be expenditure in health services on a quarterly basis. So that graph can help you have an understanding of what's happening in terms of expenditure. Can tell that in Q3 there's the highest expenditure. Then you may need to explain why you find that kind of a pattern. If you are looking at a practical situation, Q1, why that data presents with the lowest a kind of an expenditure. So when you look at any presentation like that graph, you need to be able to understand the phenomenon that is generating that kind of data, so that you can make planning, you can plan, you can make decisions, you can even come up with policy frameworks based on what you see in the data. You can also summarize our data using numeric descriptive measures like the mean X bar and the variance X squared there. So that these they typify what is important characteristics in the data. So descriptive statistics involves presenting data, characterizing that data, so that we can describe the data. So for us to be able to properly utilize the different descriptive techniques, first thing is to understand the different types of data that we encounter. So data can come in the form of numbers or come in the form of non-numeric quantities. So when data is in the form of numeric numbers, that is quantitative data, because we are quantifying measures, we are quantifying commodities. So basically there are two types of quantitative data. We have continuous data and discrete data. Continuous data is that data that falls within a continuum. It's continuous, there are no breaks. So examples of data that, follows, that is described on a continuous scale is weight is measured on a continuous scale, height is measured on a continuous scale, systolic blood pressure, viral load, blood sugar, cholesterol level. You can think of many variables that we can, categorize on a continuous scale. And discrete data is also numeric data that, it's usually in the form of, integers. So that's, described by finite number of, possible values, examples, shoe size, number of brothers. So how do we distinguish continuous data from discrete data? So continuous data, we measure continuous data. But discrete data is count data. So when you are dealing with discrete data, you know that you are counting number of patients seen at a facility on a given day, continuous data, so we measure. So that's the basic distinction between, so when you ask to define continuous data, we can say that's data that falls within a given continuum, or data that can assume any value between two, fixed points. That's, a continuous data. Then we also have non-numeric data that is defined as qualitative or categorical data. This data occurs when an individual can only belong to one of a number of distinct categories, such as gender can be male or female, level of education can be primary, secondary, tertiary, or no education. So that's or disease severity. It can be mild, moderate, or severe. So that's categorical data. But again, within categorical data, there are two broad categories of that data. We have nominal and ordinal data. So nominal comes from the word name. You're assigning values to categories on the basis of name. So for example, blood group can be A, B, or O, or marital status, the end of those categories of marital status, so with nominal data, you're basically using names to assign values to variables. But if you look at the values assigned to those variables in the nominal scale, there is no order, there is no better than or worse than. Values are just assigned on the basis, of name. And in addition to that categorical data, we also have ordinal data. So ordinal data is the qualities of the nominal data, but is the additional property of order. So in the ordinal scale, ordinal is from the word order, which means you can assign the values in order. For example, disease severity, severe, moderate, mild, none. Disease staging, advanced, moderate, or mild, there's that property of order. Although we are using names, but again, there's that, property or quality, of ordering the values, in a certain order. So that diagram there shows us the basic types of data that we encounter. So on the left there, we have categorical data, that is qualitative data, nominal with no ranking, no order. With ordinal data, we can rank in order, of importance, in order of severity. With numerical data, which is quantitative data, we have discrete and continuous data. So there are also two broad categories of discrete and continuous data: interval data and ratio data. So with interval data, variables measured on the interval scale do not have a true 0 point. So an example of a variable that is measured on the interval scale is temperature. So temperature, I'm saying that variable does not have a true 0 point, because the zero, if we are measuring temperature in degrees Celsius, for example, a body we say it's at 0 degrees Celsius, that does not imply absence of the quantity being measured. But when we say 0 degrees Celsius, we We don't imply absence of temperature. It's just, an arbitrary, demarcation where that, if you change the unit of measurement from degrees Celsius, for example, to a Kelvin temperature, for example, find that that zero is no longer a zero. So that's not a true 0 point. But, and again, with interval data, we cannot calculate ratios. Ratios calculated on the interval scale do not have any practical meaning. And again, with numeric quantitative data, we also have variables that are measured on the ratio scale. So variables measured on the ratio scale have a true 0 point. For example, weight is measured on the ratio scale. So if your weight is an assignment of 0 grams, 0 kilograms, that implies absence of, there is no weight. Even if you change from grams to kilograms to micrograms, that measure remains a 0. And we can also calculate ratios on the ratio scale. So BMI is also measured on the ratio scale. So ratio scale is a true 0 point. And again, we can compute ratios on that. So it's important to understand, the different types of data that we handle in research so that we manipulate that data using appropriate techniques. Because if you do not know, the type of data that you're handling, there is the risk of employing incorrect statistical procedures and leading to wrong, conclusions, based on, mishandling the type of data that you'll be dealing with. So all these different types of data, require, different approaches in terms of synthesizing to generate, information. So the most basic, descriptive, statistical analysis that we can handle, that we can deal with is univariate analysis. Univariate from one, so univariate, that's one variable. So when you are looking at univariate analysis, basically, trying to understand what's characterizing a specific single, variable. So this involves the examination across case of one variable at a time, and there are three major characteristics of a single variable that we tend to look at. And look at the frequency distribution, in the form of graphical presentation. Can look at measures of central tendency or measures of dispersion or measures of variation. So we can describe all these three approaches so that we have an in-depth understanding or feel of the variables that we'll be looking at. Whenever you collect data from individuals, from patients, from study participants, you need to have an understanding of how the variables are distributed in terms of distribution, in terms of central measurement, in terms of again a variation. So all these measures we need to have an understanding. So when we look at a frequency distribution, we're basically looking at the number of times or the frequency that each value or group of values occur in a study. So when we look at gender, for example, so gender is one variable with categories males and females. You may want to look at how many times you have males, how many times you have females, and you can describe in terms of the occurrence of each group. If you are looking at level of education, you may want to say what proportion in the study population is tertiary education, secondary education, primary or no education at all, so that you have an understanding of the distribution of your study participants by the variable of interest, and again understanding the number of individuals that appear in each category. So the frequency distribution gives us a pictorial view of the way our variable in terms of categories distributed. So we can also, frequency distribution, we can display it in tabular form, in the form of a table or in graphical form. So depending on the type of data that you are looking at, you can use a bar graph, a pie chart, a histogram, frequency polygon, or even a line graph, again, depending on how the variable is characterized and how the data would have been, collected. So it is the type of data that you are handling that determines, the type of graphical presentation that you are going to be using in order to have a pictorial, view of your data. So with categorical variables that are qualitative in nature, we normally describe them using a table or a bar chart. So that example that you see in the table there shows the number of times, individuals who have been staged, for a given disease, or that's ovarian cancer example. So stage 1, stage 2, stage 3, and stage 4, the number of individuals, in each stage, and again, so we can present the same counts as percentage so that you can have good feel of the way those numbers are distributed. So if you are having that, you can see that most of the patients there diagnosis are in stage 3 of disease, which is 58%. So that can actually help you understand the way patients diagnosed with ovarian cancer are distributed in the population. That's an ordinal scale. For stage, you can place in order. You can actually place in order there from stage 1 to stage 4 there. So that's an ordinal, variable stage of disease. You can use a bar chart. So it's just like, a bar chart describes, shows the frequencies, for the number of individuals in each of the categories of a given variable. So that example is showing toxicity grades, at switching zygote at 48 weeks, first line, second line. So toxicity levels is measured there in cholesterol level. So that's a bar chart. So provided that data has been put in categories, less than 5.2, 5.2 to 6.2, then of course greater than 7.8. You can show that graph. You can also, continuous data can be converted, to categorical data where you have categories, by intervals, then you can describe that data by way of, a bar chart. So that, frequency numerical variables for a frequency distribution, we can also use a histogram besides a bar chart. So histogram is usually for continuous data. And the difference between a bar chart and the histogram is that a bar chart is good, it's for categorical data, and a histogram is for continuous data. So in a histogram, it's continuous. No spaces between, the bars. So you have distribution of case subjects by parity. In an ovarian cancer study there, they are showing, parity there from 0 to 10 by way of a histogram. The vertical scale is showing the number of participants in each of those, levels of parity. Frequency polygon also shows us the distribution, of study participants by using a graph that looks like a polygon and uses the area under the graph, under the line of a histogram, within the bar. So you can superimpose a frequency polygon on a histogram. So that blue line there that you see on that curve superimposed on a histogram. It's indicating a frequency polygon superimposed on a histogram. So all these different types of graphs, they help us, have an in-depth, view of the way, variables of interest are distributed. So that's showing the birth weight in kilograms. So you can see that most of the babies there, the majority. So that's, you can say that's a symmetrically distributed distribution, showing the distribution of, birth weights, in a given population. So besides graphical techniques, so graphs, they are not adequate on their own to really give us what is typical, in a given data set. We also need numeric descriptive measures that give us, typical measures to have an understanding of the way, data is distributed in terms of center and in terms of variation. So these numeric descriptive measures that show us the center of a data set, what typifies the center of a data set are called measures of central tendency. So a measure of central tendency is an estimate of the center of a distribution of values, and there are three commonly used measures of central tendency: the mean, the mode, and the median. So they basically, and each one of these measures, depends. The use of these measures depends on the way our data is characterized. So our data can either be symmetric, if it's bell-shaped, or it can be skewed, if our data contains extreme values on one side. So if data is symmetric, then we can use the mean as our measure of central tendency. But if the data is skewed either to the right or to the left, then the mean is not a good measure of central location, because the mean is sensitive to extreme observation. So if one tail of a unimodal distribution is longer than the other tail, then the data is skewed, meaning that the data is not spread evenly. So the data can either be right skewed or left skewed, depending on which direction we have extreme values. If extreme values are on the left-hand side, you know that the data is a left skewed. If data has extreme values on the right-hand side, then we know that data is right skewed. And when we graph that kind of data, we see that we see a long tail on one end of the distribution, of that data set. So selecting the best measure to use for a given distribution depends on the skewness of the distribution and the intended use. So that diagram there is showing us three different types of distribution. So on the center there, B there, we have a symmetrically distributed a graph which is bell-shaped and symmetric. On the right, on the left there, that graph A is right skewed because we have a long tail on the right-hand side, and that C there, the C graph is left skewed because we have a long tail on the left-hand side, meaning that we have extreme values on the right-hand side. So the graph helps us to really see how our data is distributed. So it's usually advisable when you're dealing with continuous data. First, if we want to decide on the measure of location to use, to have a graphical presentation of that data so that you have a physical, a feel of the way your data is distributed. And that can inform you also the appropriate measure of central tendency to use. When our data set is symmetrically distributed, the mean is the most appropriate measure of central location. So the mean is the average of the data, and it's calculated by taking the sum of all the values in the number in the data set and dividing by the sample size. So example, utilizing the mean, we have those values which are test scores. We have 8 observations, and the sum there, if we add them, we'll get 167. So the mean value is 20.875 there. So the mean is the best descriptive measure for data that is symmetric or normally distributed. Why? Because when we compute the mean, each value in the data set contributes to the computation of the mean. So, but when the mean if data set is not symmetric, or data is not symmetrically distributed, the mean is not a good representation of center because the mean is sensitive to extreme values. It is greatly, affected by extreme values. So when the data set is extreme observations, the data is skewed, the mean is not a good representation of center. So in the case where data is skewed, the median is the appropriate measure of central tendency or central location, because the median is not affected by extreme observations. And the median is the middle number in a data set that has been arranged in order of size. So when you want to compute the median, arrange your scores or your values in order of size. It can be either in ascending order or in descending order. But it's always good to check the data set in descending order. So from the lowest, to the highest, and identify the middle number. So in this example, there are 500 scores in the list. Score 250, which is the middle number, would be the median. If we order that example of 8 values, we get that ordered sequence there. So there are 8 scores, and the value at number 4. So at the middle position there, when we have 8 scores, we don't have a value. But again, so number 4, value at number 4 and value at number 5 represents the sender, and by coincidentally is the same value 20. So the average or the mean of the middle 2 numbers give us the median. So usually, if the data set, is an even number, of values of observations, then the middle number, the middle 2 numbers, the mean of the middle 2 numbers give us, the median. But if we have an even, an odd number, of values, then the value at the middle position will identify the median. So the median is a good descriptive measure when the data has extreme values or when the data set is skewed, because it's not affected by extreme values or outliers. But again, because the median is just identified by its position, you can see that when we identify the median, we have no idea of the magnitude of the other values in the data set. So the median was just identified by sender, say that it has less statistical properties, in use in terms of data manipulation, because of, but it's just basically easy to identify. That's one advantage of the median, but it is that weakness that we cannot do, much of statistical manipulation using the median. Again, the mode is another important measure of central location. So the mode is the most frequently occurring value in a given data set. So you can identify, the mode by the number of times each observation appears in a given data set. The value that appears the most number of times identifies the mode. So there are situations where you see values, commonly repeating themselves, you can identify that, or that's a common value that you can report. So if you are looking at times to recover, for example, from a given disease, or hospital duration stay for patients with a certain condition, if most of the patients, spend some specific given number that is commonly occurring, so that you can identify that as the hospital duration time for individuals with a given condition. So in that data set, 15 occurs the most number of times, 3 times. So that's that is the mode. Our data set may be multimodal or bimodal. We have 2 numbers, for example, 2 values that appear the same number, of most times. We have 2 values with the same highest frequency, then our data set can be bimodal. Our data set can also be multimodal when you have more than 2 values that appear with the same highest frequency. Then we have a data set that is multimodal. Or our data set may contain no mode at all. When all the observations or when all the values appear with the same frequency, then we can conclude that our data set does not contain a mode. So you need to identify again. So, what informs you in terms of what measure to use, the way your data, is distributed or characterized. So a general rule to follow is that if the data is skewed either to the left or to the right, the median represents the data better than the mean. But if our data, is symmetrically distributed, then we know that the mean, is a good measure of representation of central attendance. And the mean also, because all the observations in the data set, they are utilized in computing or in the calculation of the mean. So the mean has lots of statistical properties. So you find that when we move to inferential statistics, the mean becomes the cornerstone, of all statistical inquiry when it comes to continuous data. But again, measures of location, again, they are not adequate on their own in typifying our data. We also need to understand the amount of variation that exists in the data set. So measures of dispersion or measures of variation, they tell us the amount of variation or the amount of spread in a given data set. So again, we have three broad measures of variation that we can use or that are utilized. So we have the range, the interquartile range, standard deviation as measures of variation. So measures of variation, they tell us the amount of spread in the given data set. So if there is no spread in our given data set, then that means all the observations are appearing, with the same measure. And once that happens, we know we are dealing with a constant. So, but for variables that we typically encounter, there's always, variability in the measures of interest. Even for individuals born on the same day, you measure, variables of interest, weight, you measure height, you measure all the other quantities, and you find that there's always, variation that exists, in variables in different individuals. So typical measures that we use, are those measures, given there. So the range is the simplest measure of variation that we can encounter. So the range is the difference between the smallest and the highest value in a given data set. So the maximum minus the minimum value give you the range. So the range is calculated by finding the difference between the maximum value and the minimum value in the set, which is maximum value minus minimum value. So if we look at that example, incubation period of hepatitis A patients from different experiments. So if you are given those values, so you find that the range is 31 minus 15, which is 16 days. So there's that spread, of the range of the incubation period. So you see that there's variation there in the incubation period of hepatitis A, from those experiments. And so usually interpreted as incubation period for hepatitis A range from 15, to 31 days. Percentiles, they also help us understand, the amount of variation in a given data set. Percentiles from the word percent, which is 100. So dividing a data set into 100 equal parts. So a percentile is the value that is, a given percentage of observations falling at or below it. So if we look at the 90th percentile in a given data set, means that 90% of the observations fall at or below that 90th percentile value. So if we look at the data set, we say the median is the middle value in a given data set that has been arranged in order of size. So the median is also the 50th percentile in a given data set. So besides percentiles that divide a given data set into parts, we also have quartiles. And quartiles divide a given data set into 4 equal parts. So we have the 25th percentile, which is defined as the first quartile. The median, which is the 50th percentile, is the second quartile. And then the upper quartile, which is the 75th percentile, is the third quartile. So each quartile includes 25% of the data, and the cutoff for the first quartile is 25%, the second quartile is 75%, and the cutoff for the third quartile is 75%. So these are, important values when we trying to characterize the distribution, for our data set. And the range between the first quartile and the third quartile is known as the interquartile range. So the interquartile range defined by IQR. So it is a measure of spread most commonly used with the median, used to characterize the spread of a skewed data. So when you report the median, if a median is your measure, of central location is the measure of choice, you also report the interquartile range. So the interquartile range is the difference between the 25th, which is the first quartile, and 75th, which is third quartile in a given set of data. So it represents the central portion of the distribution from the 25th to the 75th percentile. So basically, the interquartile range contains 50% of the data set. And I said that we use the median if we discover that our data set is kind of skewed, either positively or negatively skewed. So when you report the median, reporting the interquartile range, so the distribution of the data in the interquartile range, will exclude those data points that are causing skewness in the data. You find that if you just graph the data within the interquartile range, in most cases, it will be symmetrically distributed. So the idea is to report that middle 50% of the data, with the median. So for example, antibody titers range from 25 to 345 nanograms with a median and an IQR of a median of 100, IQR of 61 to 159. So the idea is that the lesser the variability, the more accurate the estimate related to the measure, of variability. So the middle 50% of the observations will have less, variability. So that graph there, it's showing us the distribution of, data sets in a symmetrically distributed data set, where the middle 50% there represents the interquartile range. And below the first quartile, we have 25% of the data set, and above the third quartile, you have the other 50% of the observations in a given data set. So the range, the interquartile range, they give us the relative position of values or observations in the data set. So when you use the range, you are basically making use of the extreme values in the data set, the maximum and the minimum. The range is sensitive to sample size. As sample size increase, the range may, dramatically also change, because the maximum value and the minimum value may also change as you increase sample size. So you find that the range is sensitive to sample size, and it only makes use of those values at the extreme ends. So we have no idea, again, when we use the range, of the other values in the middle component of the data set. So again, in the ranges, doesn't have much of statistical inquiry in it, because we're just using the extreme values in the data set. The standard deviation is the most commonly used and most informative, a measure of variation in a given data set. The standard deviation is used together with the mean. So when you use the standard deviation, you are basically measuring the amount of variation that exists in a given data set relative to the mean. So it describes the average distance of all the observations from the mean in a given sample, so that we understand, the amount of noise that exists in a given data set. So a large standard deviation represents a widespread because the observations are far from the mean. So if the standard deviation is zero, that means we are dealing with a constant. All the observations will be having the same measure. But in biological systems, there's always variation, in the measures that we encounter. For example, the mean serum cholesterol level for 4,235 men, was 213 with a standard deviation of 110. So that standard deviation of 110 there, indicates great variability in serum cholesterol level in that, group of individuals, right? So variation, so if you look at that standard normal curve there, under the normal curve, the amount of variation, the amount of data that exists for a symmetric distribution within one standard deviation, within two standard deviation, within three standard deviation. So that's typifying the empirical rule for the distribution of data, in a symmetrically distributed curve. So the empirical rule states that about 68% of the observations in a symmetrical, in a normal curve, lie within one standard deviation of the mean. So the mean is the central value there. In a symmetrically distributed data set, the mean is the central value. Again, for a normally distributed data set or symmetrically distributed data set, the mean, the mode, and the median, they are at the same position. So the mean is the most, appropriate measure of location for a symmetrically distributed data set, because it makes use of all the observations in the data set in its computation. So about 68.3% of the observations lie within one standard deviation of the mean in a symmetrically distributed data set, and about 95.5% of the data lie within two standard deviations of the mean, and about 99.7% of the data lie within three standard deviations of the mean. So that's the characteristic of the empirical rule for a symmetrically distributed data set. So how do we report descriptive measures? Always give numerators and denominator calculations. So, for example, when you are reporting that 25% of the observations were in a certain category, you need to see the denominator. So the numerator, so you report both the percentage and the counts in the data set. 650 over 2,596. So that's 25%. And when sample size is greater than 100, report the percentage to not more than one decimal place. So this is just a guide. For sample size is less than 100, report percentages as whole numbers. Sample size is less than 20, consider reporting the actual counts rather than the percentages. So the cutoff 20 of 20 there indicate a small sample size, but that's just average. And this is just a guide, it's not cast in stone. You can always, vary the way you report these numbers, depending again on the data set, on what area, you are reporting your data on. So for continuous data, we have a data set that is approximately normally distributed, symmetric. So the mean is the measure of choice. So when you report the mean, you report together with the standard deviation. So you see that when you are reading journal articles, whenever the mean is used as a measure of central location, it is reported together with the standard deviation, so that you have an appreciation when you use the mean of the amount of variation that exists in the data set. The data is not symmetrically distributed when data set is, skewed. You report together with the interquartile range. So that example, the antibody titers range from 25 to 347 with a median of 100 and the interquartile range of 61 to 159 there. So the interquartile range, 61 will be the lower quartile and 159 will be upper quartile, Q1 and Q3. Right, and I'm saying do not summarize continuous data with the mean and the standard error of the mean. We report the mean with the standard deviation. So other ways of presenting, data in terms of graphical presentations, different types of graphs depending on the type of data that you're handling. You can use those graphs, pie charts, scatter plots, box plots, line graphs. Again, all these depend on the data that you are handling. So there are various graphs that you can use. That's a scatter plot. That's showing us, scatter plot is for continuous data. Indicates that there's a strong relationship between these two quantities, FVC, increase in magnitude with force expiratory volume there. So if you draw a scatter plot there, it gives you the general relationship between these two continuous variables. So you can see that there is a general increase, in FVC with FEV there. So a picture, helps you get to grips with the way, your variables are characterized. An example of a box plot there. So use summary measures. You have the mean, you have the minimum value in the data set in a box plot, the maximum value in a data set, the median, and the interquartile range, which is Q1 and Q3. That's an example of a box plot that shows you the way the data set is distributed. When you look at that data set, you can see that there's an extreme value there in the data set. That maximum value of 49 indicates because there's a long stretch from the box there, from Q3. So the interquartile range from Q1 to Q3, the middle 50% of the observations. Look at the distance from Q3 to the maximum value. So that's an example of a data set that has got extreme observations. It is right skewed there. So box plot also helps us to see the way our data set is characterized. A line graph for data that is measured over time. You can present data as a line graph so that we can see trends over time. So reported cases of salmonellosis, per 100,000 population by year. You can see that there's an interesting peak around 1987. So you may need to explain that peak, and that graph indicates that there was an outbreak caused by contaminated, pasteurized milk during that year. There was that spike. So whenever you look at the graph, you need to explain, unusual occurrences that can be defined by sudden spikes. Then you may need to really explain why that phenomenon is being seen. So these days, if you look at the presentation of the dashboard for COVID cases over time, you can also see on the dashboard that's being presented by the Ministry of Health, also using a graph, number of cases cumulatively, a number of cases from the time of the outbreak in Zimbabwe on a month-by-month basis. Then you can see how, the cases, are being characterized, over a period of time. Then you can identify, periods when we have a spike in cases, then you may want to explain that. So that's the end of this brief discussion. So on different types of data that we encounter and the descriptive measures. We've talked about measures of central location, measures of variation, and the data presentation techniques that we use, again, either in the form of tables, in the form of graphs, and all these are guided by the different types of data that we encounter, from quantitative data to qualitative data, and all the other broad categories of the data types under those broad umbrella terms. So yes, you can also read on the different types of data, different types of graphs, and you can use as you handle different types of data that you encounter in your practice. So it is important to understand as you routinely go about your practice, understand the type of data that you record from the patients that you see, so that you can characterize the treatment outcomes, you can characterize the symptoms that patients present with, you can characterize the types of patients that you are seeing by gender, by age. So there are so many variables with which we can characterize the types of patients that you are seeing, disease severity at diagnosis, for example, the vital measures that you take at diagnosis, can characterize your patients in terms of all those things. So there are massive amounts of data that we can, play around with as we do our routine, patient care And as we think about, research persons, also need to understand when we're trying to understand a phenomenon that we are seeing in patients. You could be talking about patients that are seen with severe COVID. For example, patients admitted with severe COVID. You can characterize them in terms of so many things. By gender, for example, what is the age distribution of patients admitted with severe COVID? Where are they coming from in terms of location? You can characterize them in terms of, other, secondary issues like, comorbid conditions. What other conditions do these, individuals who are, admitted with severe, COVID, do they have any other, disease conditions that could be causing, severity of, COVID in them. So think about your practice, what type of patients you see, what kind of, treatment outcomes, patient outcomes that you encounter in your practice. You can use some of these, different types of descriptive measures and data presentation techniques, to generate information about the patients that you see in your practice. Any questions for today? I want to stop here for today. So this is our only lecture for today. I'll stop here. Then we will see how. So tomorrow we are meeting again. Tomorrow is Wednesday. We are meeting on Thursday. Tomorrow we are not meeting. So we meet on Wednesday to start on inferential procedures where we talk about, estimation, and then we will discuss principles of hypothesis testing. Right, any questions? So if there are no questions,
and you all deal with cancer patients. So my task today was to take you through principles of chemotherapy and principles of radiotherapy. I found it very useful. Yeah, just for your own information, when I actually joined the department, the oncology department in 2012, when I was starting my ichemmed, I had never been in that department, even during my undergrad. And I found it more useful, especially hands-on. At times you might read about these things, but as long as you are not practicing those, they won't stick. And that's why I always prefer to take it more practical. So discussing what we do, what is more relevant in our situation, and what we do at our center is actually going to be more helpful. And definitely I would want to take it on the more basics of what we do. So if you may allow, I may actually just start with the principles of radiotherapy. And I would appreciate it if you can also interact so that you can be asking questions, because at times I may say things I might overlook, some of you might not even know. Like I'm telling you, 2012, that's when I joined the department. And it was my first time working with radiotherapy. Yeah, so starting in terms of radiotherapy, I'm sure even in your class, you don't have those guys in doing oncology, because there are other basics besides the basic sciences that we do on the general medicine. There are more other basics on the side of radiotherapy, to include the physics and also the radiobiology, which is actually the basis of what we do when you are doing the chemotherapy, the radiotherapy. That is more of the basics. That's why we even concentrate on those more than the other basics. We actually supposed to do other basics on our own, but our main basics focuses on the basics of radiobiology and also the chemotherapy. So when you are doing radiation therapy, yeah, we are using somebody's asking me about showing the slides. I think I said it when I started this lecture. Are you hearing me, all of you? You guys. Can you hear me? Hello?
Yes.
We can.
Yes, we
Yes.
can.
Yeah. I said something about the slides. Somebody is asking much about the slides. I can give you, I didn't want to follow on the slides that I borrowed. So I'm taking you through what I want to say first. We can go through those slides later, but I'm telling you what I want to do for the lecture, for like what we do at our department and focusing on the principles, how we apply those in treating our patients. Can you hear me? Okay.
Yes, understood.
Yeah. So when you're talking about radiotherapy, we are treating patients using ionizing radiation. So definitely we have to know the spectrum of radiation that we use. So when you're talking about ionizing radiation, we are mostly focusing on the X-rays and on the basics on how we use those X-rays and at our center and anywhere else where radiation is done. I know everyone is actually scared of radiation. It's treatmental, but it can also be used for treatment. So radiation, we generate these X-rays using our machines. These are the ones we call the linear accelerators. Linear accelerator in the sense that we generate those X-rays from a source using tungsten. They are accelerated, they hit a target, and after hitting a target, they generate the X-rays. Okay, so these are electrodes which are going to generate X-rays, and these are X-rays which are going to be purified, and they are going to be like in different energies. I will explain what the energy, why different energies apply to different things. Okay, so after generating these X-rays, these are the ones which are used for treatment. Whilst I'm still there, I would also want to say radiation therapy can also use the same electrons. I said we generate the electrons, they hit the target, they form the X-rays. The X-rays are used to treat the patient. But you can also use the electrons themselves to treat. It's also part of the radiation. Okay, I'm not going to go deeper into how these X-rays now are sorted so that they'll be able to treat the way you want to treat. But coming from the X-rays being formed, now we want to treat the patient. When you are doing radiation therapy, it's more of a localized therapy. That's like what you do in surgery. When you are going to surgery, you are going to a specific site that you want to target and you want to resect. And when you want to resect, that area, that tumor with a margin because of the issues of microscopic spread and the natural history of the disease and everything. There is a margin that you're supposed to give. Even when you take the specimen to the pathology report, evaluation, they also concentrate on how much was removed, by what margin, what kind of disease is it, what margin. It's the same thing that we do in radiation therapy. So it's a localized therapy. I'll take, for example, somebody is getting a resection for a rectal tumor, maybe after radiation therapy. We are going to be looking for a certain margin. But when we give our radiotherapy, when you are going to be giving like targeting just to the rectum, after targeting other areas like lymphatic drainage, we also take note of those margins and also areas that are prone to happening microscopic disease. So when you are giving radiotherapy, it depends with the site. In radiotherapy, we give it in fields, like we put our fields in such a way that we are targeting the area that we are supposed to be dosing to a certain dose. But unfortunately, we can't do that without going through a normal tissue. Remember, when you are giving radiotherapy, like I alluded to, when using linear accelerators, that is coming from outside of the body. So definitely you are going to go through the skin, the subcutaneous tissue, the muscles, the blood, let's say we are treating the cells. All those areas are going to get a certain dose. But we are targeting an area that we would want to take to a certain dose that is curative, or like in the neoadjuvant setting. I'll explain all those terms later. So when you are giving this radiotherapy, our main aim is to limit the dose to those all other areas that we are not supposedly should be dosing. We would want to limit. There's no way we are going to be treating this patient without dosing those areas. But we would want to make sure that the doses that is going to those areas, to those organs, are limited to as much as possible and to those doses that are acceptable, so that we don't have other effects like adverse effects of the treatment. I'll come back to later on how you can work out what kind of side effects can come depending on the area that you are treating. So that is the main aim of radiotherapy. And also, if you look at how things are developing, we used to do what we call 2D radiotherapy. 2D radiotherapy, meaning that we're just using the bone landmarks. We'd take X-rays from the anterior of the patient, from the lateral of the patient, and we try to use those to guide us in our treatment. So these bone landmarks are the ones that were guiding us to treat the area that we would want to treat after the treatment plan that we do. But now, currently, we are doing the 3D radiotherapy. 3D entailing that we are taking a CT scan of the patient at the site where we would want to treat the patient. Okay, so after taking the CT scan, we import it in a planning system that we have, so that we delineate the organs that we would want to spare, and also delineate the area that we would want to treat. And just on the basics, the area that we want to treat is divided into several volumes. There's the gross tumor volume, which we call the GTV, which is the gross tumor that we see, that can also be seen on the scans. This is the gross tumor that we are going to be taking to the highest dose. Okay, because that's the area that we would want to concentrate on. Besides the gross tumor volume, like I was saying, in surgery, you have that margin that you give for the microscopic disease. In our case, to cater for that microscopic disease, we add a margin depending on the tumor that you are treating, depending on the pathology that you are treating, depending on the site that you are treating. Okay, so there are many other factors that you consider, like in the head and neck. At times, you can be asked to say, for the CCTV, you have to include this sinus, even if it's not involved, because there's a communication that can actually lead to disease going there. So when we add that margin, we term that CTV, it's clinical tumor volume. We are taking care of the microscopic disease that is actually extending to that. Okay. After adding that CTV, we also add another margin, which is called a planning target volume, PTV. This margin caters for the setup areas that we actually give, that actually we do when we are treating patients. Remember, when you are giving radiotherapy, it's not going to be given just at once. I'm going to explain that later. It's given in fractions. You get one fraction today, you can get 2 fractions in a day. At other centers out there, you can even get 3 times in a day, as long as they are spaced within a certain period to give time for cells to rotate. Okay, so when you are going to be treating a patient just now in a certain position, you are going to treat also that patient later, and you would want the patient to be in the same position, so that your target doesn't quite go out of the field. So that margin that we add is to make sure we don't miss the tumor due to setup errors. So those are the guiding principles in whenever we are delineating our volumes. Okay, there are other like margins that we also add in terms like, say, let's say an organ can actually shift to respiratory movements and everything like that. All those are taken care of, and you can be adding those margins so that we actually ensure that we target the mass, and we also don't miss the target. So as you can see, the main aim here is to make sure we We maximize the dose to our target, but at the same time, we are not missing. We are pushing towards limiting the dose to the normal tissues. At the same time, we want to maximize the dose to the area that we want to treat. So if it was possible of delivering just a dose at once, I'm sure now you know about something like a stereotactic radiosurgery, which is something, it's radiotherapy that can actually be delivered at once. But you need, it's a highly conformal form of radiotherapy. You are going to give like a higher dose at once, but you wouldn't want to do that if you are not too sure about the target that you are giving. You may give that dose at once, but you are missing the target. Okay, but so you see that in other countries they have moved to that. We still don't have the stereotactic radiosurgery here or stereotactic radiotherapy, but that's where the things are moving, trying to be more conformal, delivering doses within a short period, even at once, depending on what we are treating. And whenever we are going to that, especially it applies for those people who have small disease that we can target at once. It's not like for our cases where we have patients with advanced disease spread with stage 4, stage 3, where we would want to treat so many areas. That may not be possible. Of course, let's take, for example, for patients with non-small cell sarcoma of the lung. We know that treatment have improved and they can actually do well on their chemotherapies, immunotherapies, and everything, but they can still develop brain mets. In that case, stereotactic radiosurgery can still be used. And they can still, even if this patient is stage 4, can still benefit from that very conformal radiotherapy that can be given to small mets that are actually in the brain. Even if they are multiple in some centers, because the advantage now is you're just targeting that area that is supposed to be treated and you're sparing most of the brain. In our case, it's not yet possible to do like radiotherapy targeted to just one nodule in one mass, like a nodule in the brain, because we are not too conformal. We only have 3D radiotherapy. Stereotactic radiotherapy is still 3D, but it's now conformed. Yeah, it's now even more advanced because it's now more targeting. It's more conformal to the tumor, and it can actually preserve other parts of the brain. Okay. So after setting the patient, I told about the fractionation of this radiotherapy. We delimited this patient, we planned, made sure that the area that we would want to treat is getting enough dose, and you are sparing the normal tissues as much as we would want. There are actually guidelines that we use to do that. There are so many other guidelines that are available. Now we want to plan to start treating this patient. Definitely would have given, I've talked about fractionation. Whenever we are treating a patient, we have an intent. What's your intent to treat of treating this patient? I would want to start by, at times we can give a definitive treatment, depending on the site of the tumor, on the extent of the tumor, the stage of the tumor. We would want to say, I would want to give definitive radiation. And that can be done even in combination with chemotherapy, in which case it will be definitive chemoradiation, let's say for cervical cancer, which is the standard. Okay, so whenever we want to treat the patient, you have to decide, is it going to be radical and curative, or is it going to be palliative? Okay, some other people actually go to say, is it symptomatic, but to actually prefer it, because if you are going to be treating just the symptoms, it means you're not curing the patient. It can still fall under the palliative. So we are saying this is a palliative case and you are going to give so many doses. So how much are you going to give in terms of the doses, and for how long are you going to be giving? It depends on that. Is it going to be curative or palliative? If it's going to be curative, we would want to give like the maximum dose that you can get. You can give. I'll give an example for cervical cancer. We measure our doses in grays. That is the unit that we measure for our own for prescription. And in that grace, when you are delivering radiotherapy per fraction, I will explain why we do the fractionation. But the fractionation can either be convectional, which is 1.8 grays to 2 grays, which is the one we use. This is the convectional fractionation. But we can also give hypofractionated regimes. Hypofractionated regimes means you are going to be giving a higher dose per fraction than this one. I hope you get me. There's hypo, HYPO fractionation. It's a higher dose than the one given in conventional. So any dose above the 2 gray will be hypofractionated doses. So these hypofractionated doses can still be used even in the curative setting, and mostly can be used also in the palliative setting. You wouldn't want to get a patient, let's say a stage 3, let's say maybe a stage 4B cervical cancer. This patient has got metastatic disease, but is presenting with the PV bleeding. Definitely would want to manage the bleeding. Okay. If you are going to, the main management for that patient, like for instance, will be chemotherapy, because this is a stage 4 disease with disease which is spread outside of the pelvis. But definitely would want to give something for local control of that bleeding. Okay, so this is going to be like a palliative radiotherapy case where we are going to be delivering the radiotherapy to the pelvis. In that patient, yes, to go for chemotherapy, which is the main therapy that is supposed to get after the standard. Okay, so whenever you are going to be giving this patient, you would want to give a shortest possible course that can actually help manage the symptom of bleeding, pain, and everything. Then you go on to the further management. I just gave just a rough example. Okay, so in that case, maybe you may decide to say, I'm going to give 10 fractions in this patient, and I'm going to go at 300 centigrades, which is the 3 grays. So you are hypofractionating so that you'll be able to control the symptoms and also go on to give further management that you are going to do. Okay, this is a bit different from where we are going to say we have a rectal cancer patient who has advanced cancer. Okay, they can't go straight to surgery, and we would want to reduce that mass before you go for surgery. So we do what we call the neoadjuvant. The neoadjuvant is before the main treatment of surgery. So we are going to give a certain dose of radiotherapy plus chemotherapy to that pelvis, including the nodal drainage, and you are going to do it at a conventional fractionation. Most often we use 1.8 grays plus the chemotherapy. Okay, and we take that patient for surgery after give. That's what we call the neoadjuvant. So I think I've explained what is the conventional, what is the hypofractionation. Then there is the hyperfractionated doses. Okay, this I would actually give an example for head and neck cancers. Head and neck cancers are fast growing, very fast growing. And what we would want to do is to hit them fast as you can. Okay, so in conventional fractionation, it can be given just like 1 dose in a day, hypofraction 1 dose in a day. Hyperfractionated doses can actually be lower than the free conventional fractionation, but you are giving more doses in a day. And so eventually you are going to even take the doses that you are going to give even higher. Okay. I wanted to explain why we do the fractionation. I alluded to our radiobiology modules that we do in oncology as a basic. So when you are giving radiotherapy, what we are targeting is a dividing cell. We are giving this radiotherapy to treat the cancer, and the cancer is one which is dividing. Unfortunately, of course, there is also a normal tissue that is also undergoing cell cycles. That's why we end up having those side effects and everything. So when you are giving radiotherapy, you are targeting a dividing cell. And we know that for the cell cycle, we have different phases, G0, G1, S phase, G2, mitotic phase, something like that. It's something that we have to have that in mind to say what fraction of our cells actually in this phase. Because whenever we are giving our treatment, even when I'm going to be talking on chemotherapy, we are targeting this dividing cell. And during that cell cycle, there are certain phases which are not actually prone to be to take up the treatment. Those cells are actually protected, let's say cells in G cell. They are not even dividing. But when you are going to give our radiotherapy, we are aiming to cause what we call mitotic death or apoptotic death. And those are cells that are actually in the cycle, especially towards the mitotic phase. So they have to die in mitotic death, but so we have to have that cell in that phase. So whenever you give a fraction of radiotherapy, whenever you give a cycle of chemotherapy, you are going to kill a certain number, a certain fraction of cells that are actually sensitive during that time. That's why we end up actually doing these things in cycle or in fractionations. And when I said they have to be spaced, they have to be spaced within a certain period, is to give time for those cells that are actually resistant in a certain phase so that they can rotate and get to a phase where they are supposed to be to be sensitive to radiotherapy. And when we give a combination of chemo radiation, we are giving a small dose of chemotherapy. A small dose of chemotherapy is meant to sensitize those cells even more. Okay, so we are going to be sensitive, trying to even push them more to be sensitive to the radiotherapy. That's why we do the chemo radiation. It's trying to push that radiosensitivity even more. Okay, so when we do the radiotherapy, we are guided by that principle of radiobiology. Yeah, some actually call them the 5 Rs, some are actually 4, 5, 6 Rs, which actually allude to that radiosensitivity. Okay, and other parameters that can actually determine whether the cells are actually going to be to take out. Okay. Hello. Can you hear me, guys?
Yes, we can.
Yo, I would appreciate it if you can just even type. Well, the times I can go on and people have questions.
Okay.
All right. So I was talking about the 5 hours of radiotherapy that you can also Google out and try to go through in terms of radiotherapy, redistribution, radiosensitivity, all those things that actually guide us. But the bottom line is what we are saying is at any given point, not all cells are actually in a phase that can actually be sensitive or actually ready to take up the radiation. Okay, so the patient started our treatment. Definitely been getting this treatment after every other day. Usually we just do one treatment at a time in our situation because of the limitations. We continually we actually continually see these patients during treatment, and at times we do what we call phased treatments. Like I was saying, let's say I'll give an example, let's say for cervical cancer. When you are treating cervical cancer, we are not just targeting the cervix. Okay, I told about these volumes that we give. We have this gross tumor that we have in the cervix, but definitely we are going to include the uterus because these things, these organs are communicating the nodal drainages, the sacral nodes, and also depending on whether they have extended the paralytic and everything. So that is also one of the things that we also have to be looking at, which is an important thing in radiotherapy, to make sure that you know exactly the nodal drainage and also the status of those nodal drainage. How do you know the status and everything? Is when we do the staging. Okay, it brings me, of course, I started in terms of the treatment and everything, but before even you take a patient to treatment, you need to stage to know what exactly are you going to do it radical, are you going to do it palliative, into how you are going to place your fields. Okay, so the staging will tell you the nodal status of all these things, of all these areas. And at times, if you give, let's say, for example, there's a cervical cancer patient who has got a mass in the cervix, maybe extending into the uterus, but has got another node, maybe in the internal iliac node region, which is actually gross. It's also a separate gross tumor volume. So at times when you give radiotherapy, you're coming from outside, you're limited maybe up to 45 because of the intestines that are there, but still, you know, the gross tumor in the internal iliac, that is gross tumor in the internal iliac also need to get enough dose. So you do it in a phase treatment to say, after getting to 45, we are going to come down and treat just that area. So we are going to do phases in treatment to make sure that we take each area to a dose that we actually intend to get. For cervix, still on the cervix, I talked about these areas, and I talked about the staging. And the staging depends with the area that you are testing. For rectal, at times we would want actually MRI even for the cervix. MRI will be the gold standard for the pelvis because we want to delineate these soft tissue masses. But in other areas, CT scans and everything can actually be enough. In our case, we did end up using just CT scan because many times people don't even afford the MRI to do the staging. CT scan, chest, abdomen, pelvis for cervical cancer. For rectum, we would actually do CT scan, abdomen, chest, then try to do MRI of the pelvis, so that at least you will be guided in terms of our volume. So staging is very important because it also guides you. It also sets a standard platform to compare the outcomes of our patients. It's also even communicating with other centers so that we know the outcomes of our patients for the stage. So you can also go and read around why we do the staging. It is very important. It's very unfortunate that at times you get a patient, he has undergone surgery and everything, only to discover that patient in actual advanced diseases was outside the said area, and already some form of management has been done. Let's say for a patient who has gone in for cervical cancer, they try to remove the uterus in block with the cervix, they fail and end up doing a subtotal hysterectomy. We have had a number of patients like that. So it is always important. It's very unfortunate. You may get a CT scan and you think that this disease is going to be resectable, even if you want B2 and everything. Then you go in but fail to resect everything, and you end up leaving the disease inside. So it is very important to make sure that every patient is actually staged. And when we do our interventions, we actually do the best at first. The only downfall is after getting surgery, and now you have failed to remove all the disease. Like for instance, that case where the subtotal hysterectomy, already the uterus is removed and there are adhesions in there, and you are going to be giving radiotherapy. Our radiotherapy will actually be limited because now there are going to be even more side effects. So definitely that's one thing you also have to know about radiotherapy. For cases that have actually got radiotherapy for cervical cancer, I'm still on cervical cancer, you treated the nodes and you boosted even the cervix, we do the boosting. I talked about the external beam radiotherapy, which is teleradiotherapy, radiotherapy coming from outside the external. And then there's also another form of radiotherapy, which is actually from a very close range, which is called brachytherapy. Okay, I'll still give an example for cervical cancer because that is the most the cancer that we have, and that is what we are treating mostly, and we have the facility for the brachytherapy. So brachytherapy is giving radiotherapy from short ranges, okay, or even within the tumor, which is interstitial. So it can be either the intracavitary, intraluminal, or interstitial. Okay, so for this cervical cancer that we are teaching, we are actually doing intracavitary. For those patients who had a hysterectomy, they don't have the cavity, they don't have the uterus, and we still do the intraluminal to treat that fault of the vagina. So why do we do brachytherapy? It's a form of boosting. I said it's that when you are treating, you are limited on the doses. For cervical cancer, we want to get up to 80. So, but there's no way you are going to get to reach to 80 coming from outside. There's a limitation of the blood, a limitation of the rectum, limitation of those femoral heads and everything. So definitely we want to boost on the area. And the advantage of brachytherapy is that it can concentrate the dose where we want to get it, and it has got a high fall off so that it doesn't go outside the area that you want to treat. Okay, so at times, there are cases where you get a patient, a very frail patient, let's say 90-year-old, whatever, he has got a very early disease for cervical cancer. Let's take for example, even if it's very early like that, some patients can actually, for patients, we are saying very early disease that can be treated by surgery.
We've lost audio.
Same here, can't hear a thing.
In this period of corona. Hello?
Yes, I can hear
Since
you.
we are in this period of coronavirus, I need to know the way you are managing your cancer patient, COVID related, and how is your department structures now? Like I can see other department where there is a red zone, where there is a theater for those ones are COVID positive, maybe they need a Caesar. So
Hello.
hello.
Yeah, I lost you. Okay, you had finished your question.
Yes, I am just finished my question.
So maybe I didn't get the last part, but definitely it's a good question in terms of how we are managing patients in this COVID era. It's very, very unfortunate, like especially in the government sector. We have only 2 centers in Zimbabwe, Mpilo and Parenyatwa. Mpilo has 2 machines, none is working at the moment. All those patients that are supposed to be going to Mpilo are coming to Parenyatwa. At Parenyatwa, we have 2 external beam machines. We have actually 3 external beam machines. Okay, only 1 is working, and it's not like in a good condition. It's working, but it's not like in a good condition. So we can't afford, especially for those patients who are testing positive for corona, for COVID, we are not able to put them on the machine up until they recover. And unfortunately, that is actually prolonging their treatment time. The thing is, if you are going to be putting those patients in that, remember, the makeup of our bankers, they are not well aerated. We are actually prone, both the staff and the patients, to that. So once the patient tests for positive for COVID, the treatment is actually stopped, unfortunately. And these patients who are on treatment are being tested after every 2 weeks. Okay, so we are saying mostly on average, our patients will be on treatment for those who are radical treatment up to 5 to 6 weeks. So you get treated, you tested for 1 week, twice, or during that time, or at any point that we are suspected that we have the COVID. Okay, but ideally, if the machines were actually working, we would actually have assigned one machine for the COVID positive patient.
Okay.
Any more questions?
Thank you for the presentation. Maybe on a practical note with regards to brachytherapy. You said that the cobalt is radioactive for a very long period, extending to years. So
yeah, it's 5.26 years, yes.
Yes. So do we retrieve it after the treatment from the patient? Roughly, how long are the periods that the cobalt stays within the patient?
Okay, a good question. So it was going to be easier, especially in showing you the real things that we do. So what we do in terms of radiotherapy, brachytherapy, I told you it's a high dose rate radiotherapy as opposed to low dose rate radiotherapy. The low dose rate radiotherapy, when we're using cesium, a patient would actually be admitted with the sources in the vaginal canal feeds to that, in the radionuclide would actually be giving its radiation for a period. Okay. In terms of the high dose radiotherapy, what we are using is it's a system called after loading technique. Okay, so if you say after load technique, it entails you putting channels. So what we do, the patient is in a litotomy position. Okay, we rape just like we are doing in evac. Okay, we sound the uterus to make sure we are putting the right applicator inside to cover up to the fundus. Okay, then we put a ring that will sit on the cervix. Okay, so these are our only channels. Okay, so we have two brachytherapy units. One is called a gyne source. It has got 5 channels. Then we have got another multi source which has got 20 channels. The 5 source can be used for limited number of cancers. The 21 can be used for even those which need many channels, like in the cases of interstitial brachytherapy, which we are not yet doing. So what we are doing is just interclavicular, like I'm saying. So we have these applicators, the ring in tandem that we are using, entailing that the tandem is going inside the uterus into the fundus. And we have a ring which has got 2 applicators on either side, one ending blindly on each. So these are just channels. Okay. And the cobalt thing, the cobalt source, in terms of size, the cobalt itself is almost like just as small as a small grain of rice. And it's housed in a lead unit. Okay, so after inserting our channels, we put channels coming from that unit, from cobalt unit, connecting it to our channels. Then we get out of the room and we remotely activate that cobalt to get out of the unit and go through the channels, first channel, second channel, third channels, and at each station, depending on the plan that we do, it actually calculates how it's supposed to stay. So it's not going to be the same for every plan. And of course, during the first time that you are using a new cobalt source, it's actually more efficient in terms of reducing that radiation. So at times, in 5 minutes, we are actually through with the treatment. But as it grows older, in our case, currently, treatment of a patient can actually go up to even 30 minutes. So it depends with how efficient in terms of radiation, because it's actually decaying, it becomes weak. So the treatment times actually increases.
Yeah. Okay. Thank you very much.
Okay.
You'll be surprised that we thought that is something that the patient takes home.
Oh, yo. That's why I was saying you should come, guys.
Thank you.
Okay. I think I'm done. If there are any questions, just feel free to get hold of me.